Ever wondered how a traveling salesman can visit all cities in a region without passing through the same city twice? Well, there's a fascinating mathematical concept that tackles this very question. Picture this. You've got a map and a mission. Your goal? To plot a course that takes you through every city once and only once. Sounds like a puzzle, doesn't it? It's a classic problem that introduces us to a captivating concept in mathematics. This concept, fascinating as it is what we call Hamiltonian paths and cycles in mathematics. So, what exactly is a Hamiltonian path? Well, let's dive right in. Picture a graph. Not a bar chart or a pie graph, but a mathematical graph. A collection of points, which we call vertices, connected by lines, which we call edges. Now, a Hamiltonian path is a special kind of path in this graph. It's a path that visits each vertex once and only once. No more, no less. To help you visualize this, let's imagine a simple scenario. Picture a quaint little town. This town has 5 key locations: the post office, the bakery, the school, the park, and the grocery store. Each of these locations is a vertex in our graph. The roads connecting these locations are our edges. Now, let's say you're a mail carrier. You start your day at the post office, and you need to visit each of these locations to deliver mail. But you want to do this in the most efficient way possible, without visiting any location more than once. This is where the Hamiltonian path comes into play. You could start at the post office, then head to the bakery, swing by the school, take a stroll to the park, and finally, end your route at the grocery store. In this case, your route is a Hamiltonian path. You've visited each vertex or location once and only once. It's important to note that the order in which you visit these locations doesn't matter. You could just as easily start at the park and end at the school, or start at the grocery store and end at the bakery. As long as you visit each location once and only once, you've created a Hamiltonian path. So, in essence, a Hamiltonian path is a path that visits all points in a graph without any repetitions. It's a unique route that takes you on a one-time tour of all the vertices in your graph without any do-overs. A mathematical concept that's as fascinating as it is practical. Stay tuned as we delve deeper into the world of Hamiltonian paths and cycles. Now, let's delve into what we mean by Hamiltonian cycles. This concept is a bit like the next level up from Hamiltonian paths. While a Hamiltonian path is a route that visits each vertex of a graph once and only once, a Hamiltonian cycle takes it a step further. You see, a Hamiltonian cycle is a closed loop on a graph that visits each vertex once and only once. Picture a treasure map, for instance. You start at one point, travel through every notable landmark, and then find your way back to the starting point, making sure you don't retrace your steps. That's a Hamiltonian cycle for you. But let's get a bit more technical for clarity. In graph theory, a branch of mathematics, we represent objects and their relationships with graphs. These graphs are made up of vertices, or nodes, and the lines that connect them, which we call edges. A Hamiltonian cycle, then, is a cycle in a graph that passes through every vertex exactly once before returning to the starting vertex. To visualize this, imagine a simple square. If we consider each corner of the square as a vertex, a Hamiltonian cycle would be a path that starts at one corner, travels to each of the other corners once, and then returns to the starting corner. It's important to note that not all graphs have Hamiltonian cycles. Some graphs might not have a route that allows you to visit each vertex without retracing your steps. But when a graph does have a Hamiltonian cycle, it provides a complete tour of the graph, which can be incredibly useful in various applications, from solving puzzles to optimizing routes and logistics. So if you think about it, a Hamiltonian cycle is just a Hamiltonian path, but in a closed loop. It's a way of visiting every place or point on a map without missing out on anything and then returning to where you started. It's a full circle journey, a round trip if you will, making sure you've covered all bases. And that, my friends, is the beauty of Hamiltonian cycles. Hamiltonian paths and cycles aren't just random concepts. They have quite interesting properties. Let's delve into these properties, shall we? One of the most fundamental properties of Hamiltonian paths and cycles is their relationship with each other. You see, Every Hamiltonian cycle is a Hamiltonian path, but not every Hamiltonian path is a Hamiltonian cycle. This is because a Hamiltonian cycle, by definition, is a closed tour, meaning it starts and ends at the same vertex, visiting every other vertex exactly once. Thus, if you simply remove one edge from a Hamiltonian cycle, it naturally becomes a Hamiltonian path. However, the inverse isn't always true. A Hamiltonian path doesn't have to start and end at the same vertex, so adding an edge doesn't necessarily create a Hamiltonian cycle. The added edge could end up repeating a vertex, which is a no-no in Hamiltonian cycles. Another interesting property is the fact that if a graph has a Hamiltonian cycle, then the graph remains Hamiltonian even if we add a new vertex connected to two or more existing vertices. This is because the original Hamiltonian cycle can still be traced, with a little detour to the new vertex and back. On the flip side, removing a vertex from a Hamiltonian cycle will definitely destroy the cycle, and the graph may no longer be Hamiltonian. This is because the cycle can no longer be completed without the missing vertex. Lastly, it's worth noting that determining whether a given graph is Hamiltonian is an NP-complete problem. In simpler terms, there is no known efficient algorithm that can solve this problem for all graphs. This makes the search for Hamiltonian paths and cycles not just a fascinating mathematical puzzle, but also a significant challenge in computer science. These properties make Hamiltonian paths and cycles a fascinating study in the field of graph theory. You might be wondering, where do we use these Hamiltonian paths and cycles? Well, the answer is practically everywhere. In the world of computer science, Hamiltonian paths and cycles play a crucial role in designing efficient algorithms. They are used in solving problems like the infamous traveling salesman problem, where the goal is to find the shortest possible route that visits each city once and returns to the origin city. In operations research, these concepts help in optimizing complex processes. For example, they can be used to plan the routes for school buses, such that each child is picked up and dropped off in the most efficient way. In the field of logistics, the use of Hamiltonian paths and cycles is indispensable. They are used to optimize delivery routes, ensuring that all locations are visited once with the least amount of travel. This not only saves time, but also cuts down on fuel costs, making the process more economical and environmentally friendly. Consider a delivery driver who has to deliver packages to multiple locations in a city. The most efficient route that he can take, which visits each location exactly once and returns to the starting point, is a Hamiltonian cycle. So, next time you wonder about the most efficient route for a delivery driver, remember the Hamiltonian paths and cycles. Let's take a moment to recap what we've learned today. We started by defining Hamiltonian paths, those unique routes that visit each point in a graph exactly once. Then, we moved on to Hamiltonian cycles, their circuitous counterparts. We delved into their fascinating properties and how they differ. Finally,